Video, we're going to continue where we left off with special integrals. This is part 2 of my special integral series, and if you haven't watched part 1, I go more into this concept in a bit more depth. So if you want to start all the way from the beginning, I have linked it in one of the corners on your screen right now. But if you think you're ready to go, then let's start. I will say that the problems in this video are a bit trickier and a bit harder than the problems in the first part. So if you're new to this, then go do the problems in part 1 and then come back to this video and we can dive into some trickier problems. But if you have watched part 1, then this is the video for you. So over here we have the same 6 formulas we discussed in part 1, and we're going to solve some integrals pertaining to these formulas. So let's actually get right into it. Alright, so our first problem is integration 1 over square root x minus 1 times x minus 2 dx. And right off the bat, I see that this is a little bit different from the formulas we discussed above. In these 6 formulas, we see that we always have some type of squared, x squared or a squared or something like that, right? But in this case, we don't have any squared, right? We just have a quadratic function in the factored form, and in order to make it a square, we can actually just expand the denominator. Alright, so now we have a square in the denominator, but we see that we have a bit too many terms. We have 3 terms over here, but in the formulas we discussed earlier, we only have 2 terms, which is one is a is a constant, one is a squared, and the other is x squared. And in my previous video, I discussed how the value of x in these 6 formulas is not always going to be x. It's basically saying a function of x. So x in this case can be like x plus 3 halves, 1/2 x minus 3. It can be anything in terms of x. It doesn't have to be just the variable x. But once again, coming back to our problem, we want to create some type of square in the denominator inside the square root. So I'm going to do that right now. So we have integration 1 over, I'm going to have that square root again. I'm going to try to complete the square, right? So we have x minus 3 over 2, square, just some basic algebra, minus 9 over 4 plus 2. So basically what I did over here, I added 9 over 4 and I subtracted 9 over 4, right? And that is because I wanted to make it a square. And if you expand this whole entire thing, you should get this answer right over here. I just made it into a square. Now we sort of see this starting to come together. I see there's a square over here. In our 6 formulas, there was also a square over here somewhere. So we're getting closer. Now what we're going to do, I'm going to simplify that part. There we have it simplified. And I'm actually going to simplify it a bit more. I know I can rewrite 1/4 as 1/2 squared. All right, and this, I think that is enough. We don't need to simplify it anymore because we see that this integral is in the form of special integral number 6 over here, which is integration 1 over square root x squared minus a squared. This whole thing is x squared, and this is a squared. A squared is pretty easy to identify because a is just a constant, so a is equal to 1/2. X in this case is x minus 3 over 2 in this problem. So as I said before, x doesn't always have to be x. X can be a function of x, and it usually is. So I'm just going to replace the values of x and a that I found. Log of x, and as we said before, x is actually x minus 3 over 2. So x minus 3 over 2 plus square root x squared. So x squared, that is just that part, minus a squared, and then that is just 1/2 squared, so that's 1/4. I'm going to simplify that. Of course, we have plus c. We can simplify whatever's in here. And this over here is our final answer. So we have our second problem here, integration 1 over square root 8 plus 3x minus x squared dx. And once again, feel free and give this problem a go. But for right now, I'm going to go over the solution. So one thing that I see is that there's a negative with this x squared. I'm not a really big fan of that, especially when we're trying to complete the square. So I'm going to take the negative out from all these terms. So I took the negative out. Be mindful that the negative is still within the square root. And now I think we are ready to start making our square. So in order to make this square, I'm going to add 9 over 4, and I'm going to subtract 9 over 4 within these parentheses. And there we go, we have completed the square. But once again, be mindful that we still have the negative sign and it encompasses everything in these square brackets. And now I'm going to simplify that part. Now I'm going to expand this minus sign. And just a personal preference, I think it is much easier if we make this term a square. And that is because we already have a square on x minus 3 over 2. And that's a good thing because that is what our special integrals formula states, because we have a square on both the terms. But over here, we do not have something squared, right? In order to make 41 over 4 something squared, we know that is just going to be square root 41 over 2 squared. So I'm going to rewrite this as this right over there. All right, and now we can apply our fourth formula. So in our fourth formula, we see that a is equal to square root 41 over 2 and x is equal to x minus 3 over 2. And I'm going to substitute those values on the right side. So we are left with equals sign inverse of x over a. X, as we said, is x minus 3 over 2. And a, we said, was square root 41 over 2 and plus c. Of course, we need to simplify this, so I'm going to take this 2 up top. So we're left with sine inverse 2x minus 3 over square root 41 plus c. And this is our final answer. All right, third problem, integration x squared over square root 1 minus x to the power of 6 dx. Right off the bat, I see that we can rewrite the denominator as something like square root 1 squared minus x to the power of 6, right? As a result, we have this square up here, and that's what most of our special integral formulas look like. But this is to the power of 6, and we need something to the power of 2. So we can rewrite x to the power of 6 as x cubed squared. And just like that, we have a squared. So we have a squared over here and a squared over here. We're almost there to our special integral formula, but the thing is, in all our special integrals, the numerator is always 1, right? We can see in 1 through 6, the numerator is always 1. But in our problem over here, we see that is not the case. We see that the numerator is actually x squared. So what can we do about that? Well, in order to solve this problem, we need to apply u substitution. And over here, we're going to set u equal to x cubed. And you'll see why in a moment, because if we take the derivative, we get du is equal to 3x squared dx. And in this case, you see that in the derivative, we have this x squared, and we also have this x squared in the numerator. So that is going to help us get rid of that x squared. And u equals x cubed, we can just replace it right over there. So let's walk through this step by step. We have integration, and I'm actually going to find the value of x squared dx, which is 1/3 du. I know that this whole part is 1/3 du, so I'm going to replace that 1/3 du over square root, that 1 squared is just going to stay the same, minus u squared. And of course, we can take that 1/3 out because it is a constant, right? So I'm just going to bring that 1/3 out. And now we are pretty much good to go. We have a 1 in the numerator, and we have the denominator in the correct form. So we can use our fourth special integral formula, and this is the same formula we used in the previous problem. And we can rewrite this as 1/3 because we're going to have to keep that constant, right? And we have sine inverse of x. In this case, x is going to be u. So we're going to have u over a. Once again, a is always the constant, 1. And then plus c. That is equal to 1/3 sine inverse. We set the value of u to x cubed. So let's actually just replace that, x cubed over 1 plus c. Or in other words, 1/3 sine inverse x cubed plus c, and that is our final answer. So fourth problem over here, integration square root x over a cubed minus x cubed dx. So just to note, the square root is over the whole entire term, not just the denominator, right? So in this case, I'm actually going to split the square root. I'm going to take the square root of the top and the square root of the bottom. And we see that the bottom looks a little something like one of these formulas over here where we have the square root in the denominator, but it's not quite there yet because we see that we have a cubed over here, but in all the problems over here, there's a square. So we need to find a way to get a square. And we can do that by rewriting the denominator as this. This is how we can rewrite the denominator as. So using the laws of exponents, we can just do 3 over 2 times 2. That gives us 3. And that is the original exponent we had. So I just wrote a cubed as a to the power of 3 squared, and same thing with x. They're the exact same thing. But now, in this case, we have a squared over here, and we're one step closer. But once again, same problem with the last problem. We have something in the numerator, and in all the special integrals formula, we have the numerator is always 1. So we have to find a way to get rid of the square root x. And that is also where u substitution will come into play. So let us assume u is equal to x to the power of 3 over 2. And many of you might say, why not a to the power of 3 over 2? Well, remember, a is a constant. So it wouldn't really make any sense putting u as a constant, right? So that's why we're going to choose x to the power of 3 over 2. So you have u equals x to the power of 3 over 2. du is equal to 3 over 2 square root x dx. Now over here we have a square root x dx. We also have a square root x dx over here. So let's actually convert this integral in terms of u. This is going to become integration of 2 over 3 du. Basically how I got that, we can solve for square root x dx, which is equal to 2/3 du, and that is how I got that 2/3 du, over square root of a to the power of 3 over 2 squared minus u squared, right? And du, we already have that. We could take the 2/3 out from the integral. Once again, it's a constant, so I'm just going to bring it outside. So 2/3 equal to, and now we are going to use our fourth formula. Again, this formula is pretty common because we have a squared, x squared, and we also have a squared and u squared in this case. So we're gonna replace the values of a, or the constant, and the values of x. So we're gonna have 2/3 sine inverse of x over a. X in this case, once again, it's u over here. So I'm just going to write u over a, which is the constant. The constant in this case is a to the power of 3 over 2. Make sure to not get confused between the a in here and the a over here. The constant in this integral is a to the power of 3 over 2 plus c. Now let's replace the value of u for x to the power of 3 over 2, x to the power of 3 over 2, over a to the power of 3 over 2, plus c, and that is our final answer. All right, so last problem, and of course our last problem will be the hardest and involving trig. So that's why we have integration sine x minus cos x over square root of sine 2x dx. Of course, we see that this is nowhere near the form we need for our special integrals. So let's try to fix that. I know that sine 2x is equal to 2 sine x cos x. In other words, I'm going to write the denominator as. Now, I do want to get a square in the denominator because that's all our special integrals are basically saying. There's a square in the denominator. And in order to do that, I'm thinking this could be the middle term, maybe. Because I'm thinking if we have something like sine x plus cos x squared, I know the middle term of this, 2ab, that's just going to be 2 sine x cos x, and that is exactly that. But in order to actually achieve this, we need sine squared x and cos squared x as well. So let's just add them in the denominator. But you will notice one problem. We added sine squared x and cos squared x, but of course if you add something you have to subtract it as well. So we could subtract minus sine squared x minus cos squared x, but you might see that this whole thing is just equal to -1, right? Like this whole thing is equal to 1, this whole thing is equal to -1. So I just subtracted a -1 from there. And now I think we're good to go in making our square. The numerator is going to stay the same. Integration sine x minus cos x over square root of sine x plus cos x squared minus 1, and I'm just going to do that squared. Because now we have a square over here, we have a square over here, we're going to apply one of our special integral formulas. We have something in the numerator when the numerator is supposed to be 1 in order to apply our formulas. So once again, we're going to apply u substitution. I am going to set u equal to sine x plus cos x so that we could substitute that for u. And du will be equal to cos x minus sine x dx, and I see something really similar. I see this is cos x minus sine x, and this is sine x minus cos x. So the signs are just switched. So I'm actually going to multiply both sides of this by a negative. So negative du equals sine x minus cos x, and then dx. This way, sine x minus cos x dx is the exact same thing as over here, sine x minus cos x dx, and that is just equal to minus du. So we can rewrite this right over here as integration. We already said that the numerator was minus du over square root u squared minus 1 squared, excuse me. And let's just take this minus out. We're left with minus integration of du over square root u squared minus 1 squared. And hence we can use our sixth formula, which is integration 1 over square root x squared minus a squared. And that is exactly the format we have over here. And that is equal to log of this whole thing. So I know that a in this case is equal to 1 and x in this case is equal to u, right? So I'm just going to replace it on the right side, that part over there. So we're left with minus log absolute value of x we said was u, plus square root x squared, in other words u squared, minus a squared, which is just 1, plus c. Let's replace u. So minus log u, we said was this one right over here, sine x plus cos x plus square root of sine x plus cos x squared, because that's what we said u was, minus 1, and then plus c. And now I'm going to rewrite this, minus log sine x plus cos x plus, I'm going to simplify this whole thing, sine 2x plus c. And one thing I noticed is that when I simplified this, I got this part, the part that was in the question. So that actually worked out pretty well. We have a square root sine 2x, just a little pattern I thought to point out. But yes, when I did simplify this part, I did get sine 2x once again. And that is our final answer.